Hey guys, welcome back. Going to continue on from the torque video into rotational inertia now. Let me just jump right in here because I want to make sure we have plenty of time to get into the classwork because it is pretty involved, but it's a good problem. I like it. So we started out with rotational inertia, with torque, and that's kind of review there. Right now we're getting into rotational inertia. So if you have a long, especially a large paper clip, go ahead and pause the video and go get one and kind of unwind it like you see here. So I'll give you a second to do that. Okay, so hopefully you've been able to do that. Unwind it kind of like this and kind of twist it around your fingers like that with this on the short side. As you do that, kind of take note as to how much kind of resistance you're getting from that. Now go ahead and repeat that motion, but flip it to where you're now doing the short side. You're swinging that around. So as you do that, kind of compare the two. Which one felt like it was easier to do? Yeah, it was the second time because you had less mass up there to be kind of twirling around. And you can kind of do that with some other types of shapes. But the essential part of this is that you just discovered rotational inertia, essentially. Because with the first shape that you used, you had more of the mass to be swinging around. More mass is more inertia, just like with a linear. More mass is more inertia. Same with rotational inertia. Rotational inertia is just going to be the resistance to moving and to stopping, because it's not just moving it, but it's once you get it moving, how hard is it to stop? Just think of, if you're pushing a heavy cart, it's going to take a good bit of force to get it going, but once it gets going, it's going to also take a good bit of force to get it to stop as well. Rotational inertia is the analog for just linear inertia as well here. And here is that link to Newton's second law, as I mentioned in the torque video. Net torque, remember torque is our force analog, equals I, which is our new variable for rotational inertia now, times the angular acceleration. So this is just straight up F equals ma. F is torque. M, mass, is rotational inertia. Remember, the mass is inertia. And then angular acceleration is linear acceleration. And see that also we can look at this in terms of the sum of the torques. You remember the teeter-totter problem that we looked at in the last video, where the sum of the torques was, one was clockwise, the other was counterclockwise. The sum was just the difference between the two. So that's that sum and the net are one and the same there. So this whole thing about rotational inertia, what exactly is this? If we look at this in terms of rotational inertia, the more of it, the less the angular acceleration. The less rotational inertia, the more angular acceleration we're going to get per torque. Going back to our rod, we've got a little bit of a different setup here. 15 kilogram mass. We have a length of 0.4 meters, and we are spinning at about this pivot point right here. So in this case, if we have a 12 Newton force and a R value, which is the distance between the pivot and the force of 0.2, we can use RF sine theta to find a torque of 2.4 Newton meters. And if from this we measure an angular acceleration of 12 radians per second squared, we can find out that the rotational inertia of this particular rod is 0.2 kilograms meters squared. And that's the units that we have there. That's just directly derived from the units there. But if we do a little bit of changing here, if we change the mass, see, we've gone from 15 to 30, and we don't change the force, so we don't change the direction of the force either, or the placement of the force, we get a halving of the angular acceleration. So same torque, but half the angular acceleration. So that tells us that rotational inertia is proportional to our mass, because we went from 0.2 to 0.4 because of that change in angular acceleration. Well, okay, how did you calculate the angular acceleration? Just hold on, we'll get to that in just a little bit. But also, if we lengthen this thing out, we go from 0.4 to 0.8 while keeping the same mass of 30 kilograms. We actually are going to exponentially decrease the angular acceleration. We go to twice the length, but we see 4, we divide by 4. We go from 6 to 1.5. So we see in this case the rotational inertia is proportional to the square of the radius. So a little bit of summary about rotational inertia here. Any object that has mass has inertia. That's true for linear and angular. And remember, inertia is just the resistance to maintaining a state of motion there. The more inertia you have, the more it's going to want to maintain a state of motion, whether that be at rest or in motion. For rotating body, that's going to be dependent upon the arrangement of the mass, that R value there. Rotational inertia goes right in with Newton's second law, and then as we said, rotational inertia is proportional to mass and the radius squared. So put that all together, we have a new formula. I equals mr squared. So I is rotational inertia, m is a point-like mass. Okay, what do we mean by a point-like mass? Just think of a mass where we pretty much just have a very nice, neat, tidy center of mass, to where we don't have kind of an irregular shape. In fact, the next few slides are going to show how that affects this formula. But if you can just kind of imagine a planet going around, that's going to be, in fact, we're going to do that in a few lessons here. That's going to be using this I equals mr squared. So this is kind of your general purpose formula here. And then r, of course, is still your radial distance from axis. However, there are other examples, and don't look at this and freak out. This is not something you need to memorize. If something like this comes up on the AP test, it is my understanding that this will be given to you as far as, okay, use this particular formula. So you see situations where you have a uniform thin rod, perpendicular axis at the end, and then this is actually pretty similar to our rod, so I'm not really sure why we use just the mr squared, but that's fine. And just some other examples that you see here that are dependent on the shape that is being rotated. All right, so I'm going to get rid of this so we can go to our classwork problem here. We're going to look at classwork 15. A particular electric drill is capable of delivering torque of amount 80 Newton meters. In other words, at its maximum settings, with a drill, the more you push the trigger in, the faster it'll go. So its maximum torque is 80 Newton meters. And it's attached to a grinding wheel with rotational inertia 1.26 times 10 to the negative fourth kilograms meters squared. And by the way, this is what we're talking about here. This is a drill with a grinding wheel attached to that. I wanted to make sure you get the visual of that. It's really important for actually being able to solve this problem. It's used to grind a surface where we have a coefficient of friction of 0.30. Wait a minute, you told us we didn't have to do friction. Well, in this case, we have to do it. It's not so much with the rotational motion, but it's part of the problem. In part A of this, what's the greatest possible angular acceleration of the wheel? And B, what is the greatest force with which the wheel can be pressed against the surface without it slowing down? That's the real tricky part of this problem. Part A of this is actually pretty straightforward. Here is a diagram of our problem right here. Let me bring this up a little bit. So we have the grinding wheel. I'm assuming a counterclockwise direction. It really doesn't matter for this purpose. And the information that we're given is a maximum torque of 80 Newton meters. There's the rotational inertia there. Our radius value is going to come from this diameter of the wheel. So it's 7.6 centimeters, which means its radius is going to be 3.8 centimeters, or 0.038 meters. And that's going to be our R value. Okay, why is that our R value? Well, if you imagine the pivot point in this case is the center, the very center of the drill and the grinding wheel. And at any point, we can imagine, because really what we're interested in is this contact point with the surface. We can treat that as kind of a point mass, so to speak. So this distance between the pivot point and any point along the outer edge here is going to be my R, my 0.038. And as I mentioned earlier, the coefficient of friction of this surface is 0.30. And that's the coefficient between the surface and the grinding wheel, actually. So the first thing we're asked here is to find the greatest possible angular acceleration of the wheel. Well, that's pretty straightforward. We just want to use that second law formula there. Angular acceleration equals net torque over, that's basically A equals F over M, is with the linear analog. And just substituting my values, and I get 635,000 radians per second squared. That's a lot, but these things do move pretty quick. Second part's the trickier one, though, and I'll be honest, I really struggle with this when I first was looking at this problem, so that's why I figured this is a good one to look at. Find the greatest force with which the wheel can be pressed against the surface without it slowing down. You really have to think about the mechanics of this whole thing. So for this grinding wheel, you obviously want it to be in contact with the surface to provide enough friction to polish the surface there. But if you push down too much, you eventually get so much friction that you can imagine you push down too much, you end up like basically seizing it. So there's a kind of a point, and I'm going to scroll down a little bit here. If the friction force is greater than the perpendicular force, in other words, the force you're pushing down on this, the wheel is going to start to slow down, and you're going to lose torque, and you're going to lose what you can be doing as far as that polishing. But on the other hand, if your friction force is less than your perpendicular force, your wheel's still going to speed up, but you haven't gotten that maximum torque out of this. So what you end up with is that butter zone where friction force is equal to your perpendicular force. And at that point, you have zero acceleration. In other words, you're at your maximum speed. Kind of, think of it in terms of like terminal velocity. Remember, that's when you're falling, your maximum speed is going to be when your air resistance is equal to the force of gravity pulling you down. Kind of the similar thing here. So we want to be able to equal out the friction force to my perpendicular force here. And here's how I'm going to do that. So my maximum force that I can push down with here is going to be found using, torque is equal to RF sine theta. So when I do that, I can get a maximum force of 2,105.3 newtons. So that's my maximum perpendicular force. So I'm going to make that equal to my maximum friction force. And when I do that, just going by the math here, I end up with to achieve this maximum perpendicular force, I end up with a normal force maximum of 7,020 newtons. So what that means is as I'm pushing down here, of course, since there's no vertical acceleration, my perpendicular force is going to be equal to the normal force that the table is pushing up with. So that's where I get this from. So from this, I can tell that if my perpendicular force is 7,020 newtons, I'm going to be able to get this maximum 2,100 newton force out of this, which is going to give me my maximum friction. If I press down any more, the friction force is going to become greater, and it's going to reduce this force, this maximum force right here. But if I'm pushing down with less force than this, I'm still going to have less force because I still have more leeway here that I can get from that. All right, so that wraps up rotational inertia. Probably going to have about 2 more of these to go in rotation, so I'll get back to you guys later.